So recursion basically, you can think of like why we're talking about recursion right now. And it makes sense because we had to see how we kind of dug deeper and deeper and deeper into a JSON object or an XML, object, and kind of going through it and understanding it. So recursion can be really useful. So let me send out this link so you guys can check it out. It's also on the GitHub. So don't feel like, oh, where'd you go? Don't feel like you have to only use the collab. You can use that part. And plus a lot of the stuff is in the curriculum itself. Most of my stuff actually comes from curriculum.
You had shared the link to the GitHub.
Did I share it? I think I did. Oh, you know what? I don't think I did. Let me share that. And I'll just share this part. This is where I'll put most of, I'll try to update this. So you might see the format change and stuff like that, but any future collab notebooks and stuff or resources, I'll try to put in here. That way it's like one condensed area and you can kind of look through. And the nice thing is that you guys are my furthest ahead cohort. So you guys will always have things that will be added that are basically with you guys as you go through. Okay. But I just shared, did I share it through the, wow, I copied it, but didn't share it. Okay. Oh, I shared it twice. Okay. Anyway, that's the link to the GitHub itself. So anyway, recursion. So what is recursion? So recursion basically is essentially we can use functions within functions. I don't know if you guys ever done like the thing where it's like recursion on Google. Have you guys done that? And it says, do you mean recursion? And then you click recursion. Did you mean recursion? And basically it's kind of like going within itself kind of deal. So that's kind of like the basis of like what recursion is. It's recursively basically calling itself over and over again. So again, functions call themselves. Not all programming language actually allow recursion. Most modern ones now do because it can be really useful. And some older languages don't actually have for loops, so you have to use recursion, which is kind of interesting. It's an alternative to looping, though to be honest, it's a lot more advanced and it's hard to wrap your brain around everything because it's just kind of like, it's just, I think, not how we normally think. But it's really good for unknown structures. So if you don't know what the structure is, but you kind of know what the basis of like how it's structured at the top, but you don't know like how deep the levels go in. For example, you can see how JSON, we didn't know how it structures. If we try doing a for loop on that, we might actually bump into a mistake or something like that. So recursion can be really useful to write programs to quickly go through, well, quickly meaning that quickly to write and go through it. For the most part though, we'll tend not to use recursion in Python as our daily because it's not optimized for that. A lot of times when we use lists or pandas or some kind of structure, it's optimized for those things. But there's certain cases where recursion does work a lot faster. It's just you gotta have to figure out, and this is more for the CS part. So if you're curious about that, definitely do some research on it. You can look up recursion and Python efficiency. And you can probably see a whole big discussion about when you can use recursion and when it's best for recursion. But for the most part, these are the biggest advantages is that it's for an unknown structure like JSON or XML. Okay, so I have a few examples. So the first thing is a sum, which is actually in the curriculum. So it kind of shows you a little bit. And there's a couple examples in the curriculum too. So the first example is using a for loop. So you can kind of imagine if I asked you guys, like just out loud, like if I told you a list of numbers, right? Well, yeah, if I had a list of numbers and you needed to do a sum, okay, how would you do that? Probably just go through each of the lists, add it up, right, and keep a track of what that total is. And that's exactly what we do with the for loop, right? So we can basically take a list in, make sure this total is 0, right? We don't have anything in the list, nothing in the total. And then for each element in my list, I can do total plus equals element, right? So basically I add whatever the elements is in that list again and again and again, and then just return the total. Of course, this will only work for integers or floats or numbers. If I tried dealing with a list of strings, this obviously would give me something very different. So be aware that I didn't do a check here, but the point is that this would work fine. In this case, I made a list of 100 numbers. Does anyone know what 1 plus 2 plus 3 plus all the way through 100 is? That's 4,950. You could do the trick with once you add the first one and the last one and then divide by 2 or something. I don't remember exactly how to do it. I used to. Some famous person, I want to say it's Gauss, that figured out how to do that, the story goes. But anyway, you could very quickly do this. For example, if I wanted 100 or 1,000 numbers, I can now add up all of that part. Okay. I guess that's actually 1 through part, whatever. Okay. So that's pretty simple. If I told you guys to write this up, it'd probably take you a couple minutes at most. Like you can write this pretty quickly. Now, using a recursive function, doing the same exact thing, adding up all the numbers in a list, you'll notice it's a little different, right? So we'll still call the same thing, but with recursion. But this time, if you look at this, we have our function, sum recursion, taking in a list, but then we do a couple checks. So basically, we say if the list is, the list length is 0, basically there's nothing in that list, then that means the sum is 0, right? That makes sense. If there's nothing in the list, sum should be 0. Note that in the curriculum, on this comparison code, it does if not like my list, okay? And basically that's because it's using the fact that this right here, if it's an empty list, if you do if, let me just show you guys. If I do if, you'll see that it doesn't print out. So basically, Python will treat empty lists as like essentially false. So if not false, it'll print out. So just know that the curriculum does this kind of shortcut, but I made this more explicit. So then you can say, oh, when the length of the list is 0, there's nothing in that list. Okay, return 0, okay, which makes sense. And then I say, well, okay, what if there is something in the list? So this is what the recursion part is. So it's like, if there is something in the list, let's go ahead and just say, all right, get the first element plus, and then we're gonna do this recursion. So the best way you can kind of think about this is, what if there's only one element in the list, right? If there's only one element in the list, we'd go through this code saying, okay, well, there's an element in the list, so I'll skip this part. I'll go here. Oh, there's only one element, so that means the very first element. In this case, let's say it's like 1, right? So this will be just 1 plus the sum recursion of my list, only the elements after the first one. So if there's only one element in the list, this will actually return an empty list, right? Just 2 square brackets, which this will get called my sum recursion up here. And I'll say, hey, all right, I have an empty list. What should I do? Oh, return 0. So this number right here will actually end up being 0. Okay. And so you can actually start making this a lot more complicated, being like, okay, like you can add multiple parts to the list. Basically, as we have more parts, it gets the very first one and adds it to whatever the sum is of the rest of the list. And basically it can keep calling itself because at the end, it'll either have an empty list or essentially just one element in the list. And then if we have more than one element in the list, it'll do that first element plus whatever's left in the list. So this is kind of the basis of recursion. And to be honest, it kind of can be a little mind-bending. It can be a little bit like, wait, what exactly is going on here? But this is kind of like the main structure of kind of going through. The main thing is basically you try to get rid of one part of it and then recall the function with the rest of your structure. So that's what's kind of going on here. And this definitely, I mean, if you haven't seen this before, it definitely takes a little bit of time to digest. So yeah, just kind of a warning. But now we can see here, if I define this, I can do the same exact recursion for 1 to 100 and I get the same answer. Well, in this case, I didn't do 1,000. So I do 1,000 now. You'll see it goes through. And you actually see, this is fun, is that sometimes, because Python's not optimized for recursion, it'll either go slower or it'll say, hey, this is way too big. In this case, you can see with 1,000, it's just too large. So sometimes recursion just does not make sense, but we can still do it with 100. And sometimes it makes sense for us to be able to recursively go through a JSON object. Okay. Any questions on this guy, on how I implemented this recursion part? Okay. I usually find like recursion's best when you like look at many examples. So I made another example here, basically trying to find the maximum value. So for a for loop, like, let me ask you guys, if I had a list of numbers, just a random list of numbers, how would you find the maximum? Like if I were to say, find the maximum, what would you do?
Just go through the list one by one and say what the highest one was so far.
Yeah, good, right? Yeah, you basically kind of go through the list, right? You say like a list of numbers here. The first one is like, okay, well, that's my maximum. The next one, oh, that one's bigger. Okay, that's my max. You keep going through, like, oh, that's smaller, that's smaller, that's smaller. Oh, that's the maximum. Okay, I'll remember this number now. And you kind of go through. So that's kind of how you can kind of iterate through the list, keeping the maximum. And that's kind of what we do with the for loop. So this is why like a lot of the code that we write in for loops usually are closer to how we think. So kind of be aware of that, right? So sorry. So we have our max loop here. You can see right here, I basically have my list. I can just say my current max, I assume there's at least one element in that list. I can say, okay, get the very first element in that list, right? It's like, okay, obviously this is the maximum if it's the only number in there, right? And then I basically go for each element in the rest of the list, 1 to the end. And I called it just potential max because it could be the maximum value. And I say, okay, if that potential maximum is bigger than my current maximum, right? Then I'll make that my current maximum. Say, okay, like my first number is 1, next number is 2. Okay, 2 is my new max, right? So I assign current max equal to potential max, and then just return the current max once we go through all the whole thing. So this is exactly how Matt described it, right? Going through, just we wrote it in code. So again, this is, I think this tends to be easier to tease out because we tend to think in this way. And we can see when we do this now, the biggest number should be 99, right? So, because it only goes to 99, right? So again, not too hard. Now doing recursion, we kind of, if like we purposely are just trying to make, in this case, we're just trying to make a recursion function because we're trying to do recursion. But note that sometimes it makes sense for us to do a recursion function. And the main thing is you have to think of like, what's my edge case? Basically, what's the thing that will stop the function? And the thing that will stop the function is going to be if I have nothing in my list, right? So this is why I have this very first if len mylist equals 0, okay? Then just return the current maximum. And so this is probably something, if you have an empty list, it's like, well, what do I return in this case? Because in here, I didn't really assume an empty list. I just said there's at least one. So it's like, okay, like what would an empty list look like? And in this case, I kind of defined, this is kind of a useful Python tool, defining infinity, negative infinity in this case. If you want positive, you just get rid of this negative part. But this allows me to have a negative infinity, and as basically there isn't anything bigger or smaller than negative infinity on the real number line. Okay, so it's nice like, oh, we have a negative infinity, so that means everything is bigger than negative infinity. So if I have any numbers at all, it'll always be bigger than this. If I don't have any numbers, then I guess in this way our maximum is negative infinity, and that's just definition. You could have returned something else, but this is kind of how you can approach it. So this is kind of like our edge case. This is kind of like our stopping case, is that if our list has nothing in it, we just return the current maximum, which in this case would just be negative infinity, okay? And the reason why I did this default value is because when I say, okay, what if there is an element in the list, okay? So let's say there's at least one element in my list. Well, that means like, let's say the number 1 is my list. Well, potential maximum, okay, potential max, it's just my very first element, so the number 1. And then if my current max is basically, or if my potential max is bigger than my current max, in this case, current max to start off with will always be negative infinity. So basically any number, as long as it's not negative infinity, will be bigger, right? So if it's bigger, then I say, okay, the new current maximum is my potential maximum. In this case, it would just be the number 1. And then return max recursion, right? My list, the rest of the list. And then I pass in what the current maximum is. That's why I had to put this default here. So when I call this current maximum now, say, okay, my current maximum is 1. The list is now empty because I only had one element in the list. So just return the current maximum, which in that case will just be number 1. Okay. And obviously now it comes in, it's like, okay, what if we have more than one number? Let's say we have 2 numbers. When we do the same thing, we go through the first element, let's say it's 1 and 2. So it's like, okay, I'll get the number 1. And then I'll say, okay, is number 1 bigger than negative infinity? Yeah, it's bigger, so let's go ahead and take it. And then I say, okay, take the rest of the list, which should only be a list of 2 now. And then number 1 goes through here, goes to potential maximum is that first element in that I just passed in over here earlier. And that's 2. Say, okay, is 2 bigger than 1? Yes, it is. Potential maximum then is 2. Or sorry, current maximum is now 2. Max recursion, an empty list now because I got rid of everything. And then passing in the current maximum, which is 2. And I'll come to here and say, oh, your list is now empty. Just go ahead and return the current maximum, which the last time we passed is 2. And basically that kind of like bubbles up to everything else. So, okay, that means this is 2. This will just be number 2. And then it goes through, oh, that's 2, goes to 2, and basically just kind of goes all the way upwards. So that's kind of like how you can envision recursion. Yeah. And then so we can see now, if this works, this should give us the number 99. And you can see, it gives us 99. Cool. Any questions on how this works? This is, again, not an easy thing to wrap your brain around, but it can be useful.
Just curious, maybe I'm focusing too much on the example, but there are functions in math library, like there is a fsum function for calculating the sum of all the numbers in a limit. Is there a reason why would be using recursion rather than using already built-in functions in different libraries?
Yeah, you
like
can.
Is there a gain in?
Yeah, so there are some functions that make more sense in recursion, and that's what we're about to actually show right now. So one is could be efficiency. Fortran, for example, is a really older language. Pure functional programming languages only use recursion. There's no for loops. So like a programming language like Haskell, which is a pure programming language, which is mostly just sort of research, will only use recursion. So what's kind of interesting is that everything you can do with a loop, you can do with recursion, but you might trade off efficiency. And Python, for the most part, is actually tends to be not as efficient because we tend to do a lot of optimizations within lists and like basically arrays. Like NumPy, if you can vectorize it, usually that's faster than most recursion. But recursion is really useful when we have to handle certain structures, especially. So this actually comes into, it's a great question, Shiv, because it does lead us right into our general structure. Yeah. And I would suggest is that if you're curious about like the efficiency, definitely like go Google and say like, Python efficiency, because I'm not an expert in it. But it might be an interesting thing that you'd be curious to look at. And if I see something, maybe I'll share it out too. Okay, but I want to show you like one of the reasons why we're talking about this is that here it comes from Learn. Basically, we have a nested list here. And let's say, for example, we just wanted to sum up and say all these numbers, just add them up. And you as a person can really quickly look at it and say, oh, just add them all up. But how do you write a program for this? And if you try to do a normal for loop, which is what Learn basically tries to show, like, okay, we have this list right here of nested lists within it, which note that the nested part, that's very similar to like how XML and JSON have nested elements in it, okay? We can say, okay, total equals 0. Let's just try to go for X and L, each element, and we try to add each one, and we try to add it up, and we try to do that, and we get an error, because what happened is that the first one, if I do a quick like print X, if I try doing this, you'll see that we first get 1, but then we get 2, 3, 4, this list, and we can't add 1 plus 2, 3, 4. So we'd have to like basically say, okay, well, for each X in there, go ahead and add up each one, which can also be kind of complicated by itself. So you can kind of see like, well, okay, let's say if I wrote this now, say, okay, well, instead of total plus equals 0 plus X, let me just do total, or so say for X and X. And it's like, okay, let me try to do like, X plus, you can start seeing like, okay, well, this is not going to work exactly how I want. Like, oh wait, I have to like form this better. It's like, oh, this isn't going to work for every edge case. So for example, it's going to fail on that very first one. It's like, oh, I can't do that. Okay, let me go ahead and figure out if it's a list or not. So you start adding these complicated parts to it, and then you're not even done. That's only for the first level. So you're saying, okay, like what if I'm going to hit like a nest within a nest, or a nest within a nest within a nest? You're like, oh, it's a lot of work. So what we can do is we can use recursion. In this case, you can imagine how complicated this function would end up getting. And that's only for one structure. If we get some other random structure, it would be hard to do. We can write this recursion function and basically say, okay, we write a relatively small recursion function and able to sum up any number of nested elements. So in here, we're just adding this part so you can see it. But say, okay, if it's not L, which is basically, is the list empty, return 0, right? There's nothing in that list, return 0. Okay, we've done this before. And then say, okay, otherwise, if a list, basically the next element is a list, we're going to basically do this sum right here, take a list plus the rest of the sum of the other list. So we have a list and a list. You're like, okay, cool. We'll just do whatever this element is plus the rest of the list. But if the list element is not an empty list, it is not a list, we're assuming it's an integer or a float, some kind of number, then we can just say, okay, get the first element plus the rest of the list, right? And so what's nice about this is that by adding just one part into our function, like if you look at this right here, that's essentially what we wrote before with some recursion, right? From like way earlier. And essentially just adding this one part right here, I now am able to look for a list within a list. So I added this extra part in here versus having to do with the whole for loop. Now if I run this, I can actually find the sum, which we'll find out is 45. And you can see here, this is just the structure. It's printing out the list. So the first L, it's just the nested list within a list, right? The second one gets that first element, number 1. It's popped it out because it's just a number. And the second part will just be another list within a list. That third one, basically, it's like, oh, it found another nested list. So it goes to 2, 3, 4, 2, 3, 4, 3, 4, 4, and then to an empty list. And then it says, okay, it pops back out to this end right here. So this right here is actually a depth first, kind of like saying we're digging deeper, 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 deeper. And then when we hit the bottom, we pop back out and go to the next element and maybe dig deeper, 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 pop back out to the next element. So, but you can see here, this is a relatively simple like function that we can write compared to something we'd have to write for a large for loop. And it's a generalized function. So if I put something like, let's say, I put like 10 here, and let's say 11, and then I put something like 12 and 13. That's a deep list, right? You can think about like how much that will basically go deeper and deeper and deeper. And we can actually still use the recursion function. I don't know why I reran this, but you can see it still is able to go through that whole thing still. So it doesn't matter how many deep layers we have, because basically it can always go deeper and deeper and deeper. Okay. Oh, I realized I'm out of time, but last part, you guys can see this. There's 2 different parts of going through recursion. It's depth first versus breadth first. And depth first is exactly what we saw right here. Again, this is in the curriculum, so you can kind of play around with that, check it out. And our breadth first is much more, instead of going deeper, 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 and then popping back out, you basically would execute, say, okay, let me get the very first layer. It's like, okay, let me get through this part. Oh, there's this thing, I'll come back to that later. Give me 5. Oh, there's this thing, I'll come back to this later. And then it'll come back to the second layer and dig into here. And then say, okay, all done with this. Oh, this other layer right here. Let me dig into this. Like, okay, first element, that's good, easy. Oh, this is a list within a list. Okay, I'll skip that, save it for later. So breadth is kind of like you're going on the same level first. And then once you're done with the whole level that you can deal with, you go to the second level. Depth first is that you go, once you hit a level, you just keep going deeper. And then once you're done with that level, then you pop back out and see what the next element is. There's a good explanation over here that the Learn links to, which is brilliant.org, which kind of shows a little bit of the difference between breadth first and depth first. Usually it's done for search terms, but I'll just quickly just show that this exists right here. This is from Learn direct. This is directly from Learn. So you can use this to kind of see what a depth for, or a breadth first algorithm looks like. And they have some comments on here too to explain everything. But it's the same, it'll proceed with the same process right here. So if I run this now, and we'll use the same list that we had, you can see here, it's only going basically breadth. It's going all this layer first, and then it's going into these deeper layers. Okay, cool.